In this video, we're going to take a look at cylindrical and spherical coordinates. So we're going to get two additional ways to represent a point in three-dimensional space to go along with our XYZ coordinates. So this is similar to when we learned polar coordinates in 2 dimensions. So in 2 dimensions, we learned how to plot points using X and Y, which we call rectangular coordinates, and then we later learned polar coordinates, where you could represent the same point in 2 dimensions using an angle and a radius. And the reason we did that is certain curves in 2 dimensions were easier to represent in polar coordinates than compared to rectangular coordinates. And the same is going to be true in 3 dimensions. So we have our XYZ coordinates that we're comfortable with, but sometimes a particular curve or surface in 3 dimensions is easier to work with when it's written in cylindrical coordinates or spherical coordinates. So we're going to start with cylindrical coordinates. So say you've got a point in 3 dimensions, so point P, and in our traditional coordinate system that we've been using, its point is X, Y, Z. So you go along the X axis, along the Y axis, and up the Z axis to that point. Well, now we want an alternate way to represent that exact same point. So we've got this point P in 3 dimensions. So we've got this distance, which is the Y coordinate, this distance, which is the X coordinate, and then this distance, which is the Z coordinate. So how can we represent that same point in a different way? Well, here's the XY plane, and if we swing an angle out to where it meets, where if you were to put P back down into the XY plane, if you were to swing an angle out where that terminal side would intersect P, the distance from 0, 0, 0, which we call the pole, out to that position we're going to call R, and then the angle made between the positive x-axis and that terminal side, we're going to call that theta. So it's actually the exact same R and theta that we considered in polar coordinates in 2 dimensions. And then because this is in 3 dimensions, we have to count for Z. Well, in cylindrical coordinates, Z is the same. So whatever Z was in rectangular, it's going to be the same Z in cylindrical. So basically it's just taking the idea of polar coordinates and then adding an up-down component, if you will, the way we draw the X, Y, Z axis. It's adding that other dimension in there, which is just Z, the same as it is in rectangular coordinates. So the X coordinate, so we have X, Y, Z, the X coordinate would just be R cosine theta, because it's just a right triangle. Just a right triangle. So cosine of that angle is the adjacent side over the hypotenuse. So X is going to be R cosine theta, just like it was in polar coordinates. And Y would be R sine theta, just like it was in polar coordinates. And then Z is just Z, because that allows us to move above or below the XY plane. Well, now we need a way to relate our X and Y and Z, not really the Z because it's the same in both coordinate systems, but the X and Y back to an R and a theta. Well, again, it's exactly like polar coordinates. So using the Pythagorean theorem on this right triangle in the XY plane, X squared plus Y squared equals the radius squared. So that relates X and Y back to R. And then tangent of this angle is Y over X, which relates Y and X back to an angle, theta. But just like in polar coordinates, there's an infinite number of angles theta that would satisfy that equation. So there are many different representations of our point in cylindrical coordinates, because this angle could take on so many different values, but yet end up representing the same exact point in 3 dimensions. Okay, so just let's practice some basic conversions. So let's say I give you an R, a theta, and a Z. We want to switch it back to rectangular, an X, Y, and Z. Well, X is just R cosine theta. So that means that X would be the radius 4 times cosine of 5 pi over 6. which would come out to be 4 times negative principal square root of 3 over 2, which would be negative 2 times the principal square root of 3. And then y is r sine theta. So y would be 4 times sine 5 pi over 6, which would be 4 times a half, which will be 2. And then z is 3. It's just the same in both representations. So we get negative 2 principal square root of 3, positive 2, 3. And that's an x, a y, and a z. So it's rectangular. So those would be equivalent points in 3 dimensions. Okay, so let's actually go ahead and take a look at that in 3 dimensions. So our cylindrical coordinates were 4, 5 pi over 6, 3. So in 3 dimensions, so this is the positive x-axis, this is the positive y-axis, this is the positive z-axis. So using the positive x-axis, we swing an angle of 5 pi over 6, which is 150 degrees, over, and that would put the terminal side here. The radius is 4, so we go out 4 units, so that's this distance here, and then we go up 3. So you swing the angle to 150, radius of 4, up 3 units, and that puts you right here at P. And then in rectangular coordinates, it's negative 2 root 3, 2, 3. So along the x-axis, you go negative 2 times the square root of 3, which is negative 3.46 about. And then you go 2 along the positive y, or in the positive y direction, and then 3 up along the z-axis. So you can kind of see how both work together here in this picture. So as you can see, P is above the xy plane, but that circle and radius are in the xy plane. So it's basically polar coordinates with the ability to go above or below the xy plane. Okay. What if I give you rectangular and we want to switch it to cylindrical? So this is an x, this is a y, this is a z. So now we want to switch it over. So r squared is equal to x squared plus y squared. So that would imply that r is either positive or negative principal square root. Let's see, 1 squared plus root 3 squared. So r is going to be positive or negative 2. And tangent of the angle we're calling theta is going to be y over x. So tangent of theta is going to be root 3 over 1. So theta is going to be pi over 3 plus n pi, where n is an element of the integers. And of course z is just 2, because z stays the same. So let's say you choose a positive r. So let's say you want the radius to be positive. So just like in polar coordinates, you can do a positive radius or a negative radius. So let's say you want r to be positive. Then our coordinate would be, let's see, r would be 2, And then we could choose pi over 3 for our angle, and then z would be 2. So that'd be a nice, convenient, relatively straightforward coordinate in cylindrical coordinates. Let's say you wanted r to be -2 for whatever reason. Okay, so you would do -2, and then if you're doing -2, remember that you're going the opposite way of the terminal side. So we would need 4 pi over 3, 2. So I would go with this one. I tend to avoid a negative r if possible. It's easier to think about a positive r. But you have more than one answer here. There's more than one way to represent that point in cylindrical coordinates. Okay, so why do they call them cylindrical coordinates? Where does a cylinder come into play? So let's see if we can't get an idea of why these are called cylindrical coordinates. You may have already kind of seen it in 3 dimensions. So what I've got here is I've got an angle theta in standard position on the xy plane. I've got the radius r. I've got a generic point in cylindrical coordinates here. So this point is just r theta z. So as I change the radius, that affects the point. As I change z, that affects the point. And then as I change the angle, that affects the point. So changing the radius, changing z, and changing the angle all affect that point. But as you can see, we have a cylinder. So the base of the cylinder is right here on the xy plane. And then depending on where z is, z could be negative and down there, if you just kind of extend that up to the point, we've created basically a cylinder. So hence the name cylindrical coordinates. Because you can think of a cylinder where our point is contained on the edge of one of the bases, and the other base is on the xy plane. Alright, so what if we have an equation that's in rectangular coordinates and we would rather write it in cylindrical coordinates? Well, let's give that a whirl. So we have x squared plus y squared equals 4z squared. So x squared plus y squared equals 4z squared. Well, we know that x squared plus y squared is r squared. So we'll sub that in. And then z is just z in both coordinate systems. So that would be in cylindrical coordinates. Now, it doesn't depend on x and y. For b, we've got y squared equals x. Well, we know that y is r sine theta. So y squared would just be r sine theta squared equals, well, x is r cosine theta. So this will equal r cosine theta. And then we'll have r squared sine squared theta minus r cosine theta equals 0. Factor out an r. And we get r equals 0, or we get r equals cosine over sine squared, which is the same thing as cosecant times cotangent theta. Now, this says that r is 0, and r equals 0 is a solution for this equation also. So r equaling cosecant theta, cotangent theta. If r equals 0, there is a theta for that. So r equals 0 is a solution of this equation and this one, so we don't need that one. That one's not adding anything to our cylindrical equation here. So r equals 0 is already a solution or a possibility in this equation. Otherwise, we would need both of those. Okay, so what exactly do these curves or surfaces look like? I mean, that's kind of like to know what these things look like. Yeah, we know how to convert them, but what do they look like in the first place? So let's look at this first one, x squared plus y squared equals 4z squared. So that would be these two cones here that meet at the pole. The vertex is both at the pole. And so we switched that over to cylindrical as r squared equals 4z squared. And then the other one that we did was y squared equals x, and it is this parabola-like object, except for extends in definitely along the z direction. And we switch that to cylindrical as r equals cosecant theta times cotangent theta. Okay, so what if we have a cylindrical equation and we want to switch it to rectangular? So we want to go the other direction. So we've got r squared cosine theta plus z squared plus 1 equals 0. Actually, let's change this. Let's do 2 theta. Let's have the argument be 2 theta for that. So cosine of 2 theta is equivalent to cosine squared theta minus sine squared theta. Thank you, trigonometry. And r squared, we know r squared is x squared plus y squared. And then cosine squared, well, we know x equals r cosine theta. So if we square both sides, x squared is r squared cosine squared. So cosine squared is x squared over r squared minus, and we could do the same thing for sine squared, so that would be y squared over r squared. So as you can see, we're going to get a common denominator of r squared. Well, r squared is the same thing as x squared plus y squared, so this is going to simplify nicely. Into x squared minus y squared plus z squared equals -1, or you could write it as y squared minus x squared minus z squared equals +1. Let's take a look at what that looks like. 3 dimensions, what the actual surface we're looking at here is. Oh, whoops. Wrong one. So here's our rectangular equation that we just created from our cylindrical one. And as you can see, in 2 dimensions it would be a hyperbola. This is a hyperboloid. Okay, so what about spherical coordinates? Spherical coordinates. So spherical coordinates, so again, we just need a way to represent a point in 3 dimensions. So say you've got a point P, it's located at x, y, and z. X, y, z. So here's our point P, x, y, z. So we're going to steal part of this from cylindrical. So we're going to do the same angle theta, where you have the positive x-axis, swing a terminal side out to meet where P would be if it was in the xy plane. Call that distance r, that theta. So that's exactly the same as polar coordinates and as cylindrical coordinates. Well, now we're going to draw a segment. We're going to think of a segment from the pole to that point. We're going to call that distance rho. So rho is always hard to draw by hand, but it's not really a P, it's rho. Call that distance rho. And then the angle created between the z-axis and rho, we're going to call that phi, or phi. I actually don't know how to say that. I don't know if I've ever heard that said out loud. So we're going to call that phi. So we've got this angle theta, this distance rho, and this angle phi. So rho is the distance between the origin and the point P. Theta is the angle used in cylindrical coordinates, or polar coordinates in 2 dimensions. And then phi is the angle between the positive z-axis and the segment OP, where O is the origin. So just as this picture shows. So that value R, right here, using this right triangle, we can show is rho times sine of phi, which we already know is also the principal square root of x squared plus y squared. Okay, so how about our conversions? So say you want to go from spherical coordinates to rectangular. So you plug in rho, phi, and theta. Multiply that out, give you x. Rho, phi, theta. Multiply that out, get y. Rho, phi. Multiply that out and get z. So that's assuming you know the spherical coordinate. You want to switch to x, y, z. What if you have rectangular and want to go the other way? So rho squared is x squared plus y squared plus z squared. Tangent of theta is just y over x like it was before. And then phi is going to be inverse cosine of z divided by the principal square root of x squared plus y squared plus z squared. Again, those angles are multi-valued. There's more than one possible angle that would work there. Well, let's say you're in spherical, you want to switch to cylindrical. So spherical to cylindrical. So you would take rho squared times sine squared of phi, multiply that out and get r squared. Theta is the same theta in both. And z would just be rho times cosine of phi, using that right triangle in the picture. Say you want to go cylindrical to spherical, keeping r positive. Rho would be the principal square root of r squared plus z squared. The angle theta stays the same, and phi would be inverse cosine of z over the principal square root of r squared plus z squared. Again, the angles are multi-valued. So it kind of depends on where you want to go, now that we have 3 different ways to represent a point in 3 dimensions. So let's practice a little. Say we have an equation in rectangular coordinates, and we want to switch to spherical coordinates. Okay, so we're in rectangular and we want to go to spherical. So we're going to use these conversions here. So rho squared is this, tangent of theta is this, and phi is this. So rho squared is x squared plus y squared plus z squared. Or another way to think of it is x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine theta. So that's how x is related, y is related, and z is related. So let's see if we can make that work. So we want to switch in we want to switch into spherical. So x is rho sine phi cosine theta, but we're going to square that. And then y is rho sine phi sine theta. We're going to square that. And then z is rho cosine phi. We're going to square that. Alright, so the left side has a greatest common factor of rho squared sine squared phi. Leaving us a cosine squared theta plus sine squared theta. Which is just 1. So we end up with rho squared sine squared phi equals rho squared cosine squared phi. So sine squared phi divided by cosine squared phi has to equal 1. So in other words, tangent squared phi equals 1. So we can stop there if we want. Of course, this implies that phi is pi over 4 plus n pi, where n is an integer. So this would be an equation in spherical coordinates. We started with rectangular coordinates. So basically it was swapping x out for the expression involving rho, phi, and theta. Same thing for y and z. Let's see, what if, let's do another one of those. So this time we have x squared plus y squared plus z squared minus 4z equals 0. So let's switch this over to spherical. So x squared plus y squared plus z squared, that's actually just rho squared. And z is rho cosine phi. So we can take out a rho. So rho is 0, or rho is 4 cosine theta. Now, rho equaling 0 is a solution to this equation, so this is not needed. It's redundant. So we end up here. So I've indicated that this is a sphere, so both of these would represent a sphere in 3 dimensions. And earlier I indicated this would be a cone of some sort. So let's go ahead and take a look at that. Let's see, let's look at the sphere one. So here's our sphere. So our x squared plus y squared, and then z squared minus 4z equals 0. I rearranged the equation a little bit. But as you can see, that is a sphere in 3 dimensions, sitting on the origin there, 0, 0, 0. And then the cone, the x squared plus y squared equals z squared, or tangent squared phi equals 1. when you graph looks like this. So we've got our two cones meeting at the origin, 0, 0, 0. So now we have three different ways to represent a point in 3 dimensions to go along with our polar coordinates that we have in 2 dimensions.